everything is recorded, so the video is recorded.
But the slides.
The slides, we don't think that they must be done. If you want.
Maybe we should tell them. I probably.
But the videos are already.
I know.
The video is already tracked.
Videos I never look at.
Much more of an expert than I am. Yeah, she has more recent results. I sent mine to Raina, but she has made more with me sessions.
If you want to talk about it,
Okay, we shall start. So our last speaker of today is Professor Priyanka Raina from Stanford. So I'm actually looking forward to this talk. All the other talks about hardware were talks that I've heard quite a few times in the past, and I think that some of them I can even give by myself. And this is the first time. No. You actually changed some of the things. But this is the first time I hear Priyanka, so I'm glad she's here, and I'm looking forward to it.
Thank you. Should I get started? Should I get started?
Yeah, sure.
Yeah, okay. Excellent. Good afternoon, everyone. My name is Priyanka. I'm a faculty at Stanford. And today I'm presenting some of the work from my research group on automated design space exploration and generation of AI accelerators. And this is a very hot topic these days because everyone is interested, as a community, we are interested in improving the efficiency with which we are running AI models today. And so part of the methodology for improving efficiency is to create better hardware for running these AI models. So to reiterate, why is this problem very interesting? This problem is interesting because AI models are growing and evolving very, very rapidly. What you see on this chart here is just the progress in the last 3 years. So on the x-axis, you see years. And it's just 2022, 23, 24, 25. So just, the last 4 years. And on the y-axis is accuracy on a language understanding task. And the chart actually goes from 0 to 100. So we started in 2022 with around 40% accuracy on this language understanding task. And in just 4 years, we have gone from 40% accuracy to more than 90% accuracy. There is hardly any other field in which the rate of progress has been so enormous. And as a baseline, as a reference, human experts on this task perform at about 90% accuracy. So the models have gone from not being usable at all to outperforming humans in the last 4 years. And a lot of this progress has come at a cost. So if you look at both the size of the models and the amount of computation you have to do to execute these models, it's enormous. So in order to get to this level of human level or more than human level accuracy, you need to spend enormous amounts of computation and enormous amounts of energy moving data. So as a result, what has happened is that every company...
The size of the sphere, does that have any meaning in that picture, the size of the circle?
It's the size of the model.
Okay, all right.
Yeah. The circles are the size of the model. So now you have to execute these humongous models, and in order to do that efficiently, you cannot rely on general purpose computing anymore. You have to design compute that is specifically tailored to the types of operations that occur in the AI models. And for that reason, almost every company is working on creating these specialized hardware devices. So efficient AI requires, these things are called hardware accelerators. And the name of the game today is who can design the most efficient hardware accelerator, as well as the software to deploy the model on their efficient accelerator. The problem, however, is that this hardware design process is quite slow. So typically, the companies were not used to the applications changing at such a rapid pace. So typically, when you are launching a new chip, say, it has to go through many different stages of design, from analyzing the application to coming up with a specification, writing an implementation at the register transfer level, testing it, then going through physical design, and then writing software. And this whole process, can take about 2 years from concept to production. And it is quite engineering cost intensive. And that engineering cost also translates to actual dollars. So designing these specialized chips is very expensive, on the order of hundreds of millions of dollars per chip. And the problem is that even if you do spend, 2 years and hundreds of millions of dollars designing a specialized chip, the AI model itself is not remaining stationary, right? So in the time that, let's say, you were designing AI accelerators for image classification, so you were using convolutional neural networks, by the time your chip is back, people are not using convolutional neural networks anymore. Today, everyone is using vision transformers. And the computation in the new model might be somewhat similar, but not quite the same as what you design your chip for. So AI models evolve. And this leads to a big problem. Now you have spent all this money and effort, and now you have a product that doesn't quite accelerate the application that you eventually want to deploy. So in addition to this, just figuring out what to design is a massive challenge. So the design space of these AI hardware systems is humongous. So for example, you have to decide how much resources to put down on your chip. So that's called resource allocation, or kind of what is the scale of the chip that you're designing, how much compute you want to have, what your memory hierarchy looks like, how many levels of the hierarchy, what the sizes and bandwidths of each of the memories are. And these resource allocation decisions affect the performance that you will eventually have, your power consumption, and your area. You also have to make some more fine-grained decisions about your resources. So what type of resources do you put? So for example, what is the precise instruction set of your hardware? What is the instruction set for matrix operations? What is the instruction set for vector operations? What precise data types and quantization schemes do they operate with? Like, are you operating on integers, small integers, floating point numbers, some weird format, some mixture of these? And then with neural networks, you also have to work with not just the type for an entire tensor. You usually have some scaling factors associated with it. What is the granularity of that? So you have to make a whole bunch of decisions around what kind of compute you want. And then finally, you have some type of compute, some amount of compute. And then the question is, how do you actually schedule your AI model onto it? So you have to make a whole bunch of scheduling decisions. Like, how do you, let's say you're doing a matrix multiply, it's two giant matrices. So you can express it as a bunch of for loops, right? So how do you parallelize those loops? How do you tile them, order them, fuse them, and so on? And all of these are very important for the eventual performance and power of your design. So the real design space of this AI hardware is kind of a cross product of all these things. Okay, so the problem statement that we are aiming to solve in this work is there a way to systematically explore this design space and automatically generate tape-out ready hardware? Okay, so now that we have set up the problem, how are we solving this in our work? In this work, we heavily use high-level synthesis. What is high-level synthesis? So this technology has existed for some time, and what it allows you to do is, instead of manually writing implementations of your hardware at the register transfer level, you can start at a higher level of specification, an algorithmic specification, and essentially use a tool to convert that automatically into lower level implementation. And typically, the specification is done in System C or C++, at a much higher level than Verilog. So what's the advantage of using HLS? What HLS allows you to do is it allows you to explore a whole bunch of those design decisions that I talked about much more easily. So for example, here's a simple loop where you are taking 4 numbers and adding them one by one. So you can do it in multiple ways. You can have one add, and you can go through these additions over multiple cycles, right? So first you add the first 2 numbers, then the next cycle you add the 3rd number, and then you add the 4th number. Or you can put down 3 adders and just get done with the whole computation in one cycle. So if I had to write these 2 implementations at a register transfer level, at the Verilog level, I would have to hand write these 2 implementations and then compare, okay, like what is the area, what is the performance and power and so on. But with HLS, what I can do is I can write this directive called a pragma, which specifies how much unrolling or parallelization you want on this loop. And you would just change one number here, and it will automatically generate these 2 designs from the same specification. So you can imagine that in a much bigger accelerator, you have numerous places at which you have to explore, like how much parallelism and pipelining and so on you want to have. And instead of writing the cross product of all those implementations, you can just sort of manipulate these pragmas and get multiple different design points. So it's much quicker to explore different design decisions with high-level synthesis.
So you do need to put the parameter number, but it's easy to change it.
Since you asked a question, Raina, in principle,
Yes.
like, I know that today's tools don't do that, but in principle, you should not need those fragments for statically schedulable code.
Well, you do need those pragmas
In
because
principle, there is no need, right? If it is statically schedulable, if you know everything during compile time, then the tool itself, the HLS tool itself, should be able to do all this unrolling and pipelining and all that. Now, unfortunately, the commercial tools like, whatever the one from Mentor Graphics, Siemens, it doesn't do that, and that's why you have to make it do.
Yeah, I think it depends upon at what level are you specifying the trade-off. So if you can, you could tell the tool, here is the area budget that I have, and give me the best unrolling that fits in that area budget. Sure, then you don't have to deal with the pragmas, right? But it doesn't do that, so we have to deal with.
Yeah, in principle, but in practice too, because now you go back to the Hercules tool, David Kuh, 1990 at Stanford.
Yeah.
He was doing these things.
Yeah,
It would unroll it and then recompress it if you didn't have enough resources.
Yeah, unfortunately, what's the catapult, right? Yeah, it doesn't do it, and that's the problem, Yeah. But anyway, go ahead. Yeah.
All the commercial tools.
Then you have to go figure out, you have 2 unroll fragments, and then it wouldn't be a decision problem, right?
The tools would, in principle, the tools would be able to do that, and the original HLS tools used to do that, but unfortunately, the commercial tools don't do that.
Yeah.
But go ahead, sorry.
So basically, the problem happens. The problem that happens is that in any realistic application, you have way too many loops,
Right.
and you have way too many design decisions that you have to make. And so right now, the tools leave it to the user to figure out which of those pragmas are important to explore, and parameterize it at a higher level of abstraction, basically.
And also the exploration is still manual.
Exploration is manual, yes. Okay. So that being said, HLS gives us still a whole bunch of advantages. So it is easier to design than designing in Verilog, because you're designing in C++ rather than Verilog, and there are a lot of meta-programming features in C++ that don't exist at the Verilog level. The other very important advantage of HLS is that it does automate the generation of pipelined implementations for different frequencies and technologies. So while the parallelism you have to explore manually, I can give the tool, hey, get my design to run at 500 megahertz in this 16 nanometer technology, and it will figure out how to pipeline your design to meet that frequency. So in that case, the specification is very high level, just a clock period, and your technology library, and then it'll generate properly pipelined code. And even getting this done at a Verilog or level is extremely difficult. Like, there's a lot of manual process. And then in that process of, because it's generating these pipelines for you automatically, it also generates all of the accompanying control state machines automatically. And if you have ever designed a complicated piece of hardware, you know that it's not the data path that is difficult to design or verify. It's actually the control that is extremely hard to verify. So if it takes away the burden of writing those control state machines correctly from you, then you get much more productive. So that comes back to this second point, which is that with HLS, we have systems that are much faster to verify. You can verify things at a C++ level instead of a Verilog level. Right? So you're not doing cycle accurate simulations, you're doing functional simulations, and that runs orders of magnitude faster. So you can test more. In the context of AI hardware, that speed has a very distinct advantage. So on a Verilog design, there is no way I'm going to run an entire data set through it and figure out the accuracy that my model will get, because it is going to take months for that entire data set to go through RTL simulation. But at HLS level, since we are orders of magnitude faster, you can push entire data set through and know precisely how much accuracy your implementation will give on a particular task. So that's very useful in the AI setting. However, not everything is so rosy when it comes to using high-level synthesis. So the problem is that it's not that you write this C++ model and push it into the tool and out comes very performant RTL. You actually have to make a lot of hand tweaks to the functional model to make it suitable for an HLS tool to consume. And the tweaks that you have to make is that you have to explicitly introduce hierarchy. So if you have, you want a certain hierarchy of modules in your design, you have to make that explicit in your functional model. You have to precisely specify all the types. You can't just say integer, because if you say integer, it will assume 32-bit integer. So you have to be precise about how many bits you want at what place. You have to explicitly specify the complete memory architecture. So while HLS tools deal with registers automatically, they don't deal with memories. So you have to know exactly what buffers you want, what size, what bandwidth, where do you want them, and so on. And then all these pragmas for loop pipelining, unrolling, etc., are also manually specified. And you have to do all this while following a coding style that the tool is happy with. So unfortunately, not all C++ is the same. So you write C++ in one way and it produces performant code, and you write it in a slightly different way, and the code is not performant. Right? So creating this model that the tool will consume is not easy for most designers. And so that has hampered the adoption of HLS in reality. Okay, so how do we get around this issue? We want to use HLS, but we still want to, make it accessible. So the way we get around this is by, we know what works with HLS. So we create an AI accelerator template in high-level synthesis that follows all of these rules that make the tool produce performant code. And so when you're designing AI accelerators, you're not designing something arbitrary, right? AI accelerators have some structure already. And this template encodes that structure. So for example, a lot of the times, your computation is dominated by matrix multiplications and convolutions. So, a systolic array is good at doing matrix multiplications and convolutions, so you explicitly encode a systolic array in this template. And then these matrix multiplications and convolutions are followed by some, vector operations, nonlinearities, and so on. So you have some sort of vector pipeline that I'm showing here on the right that does those operations. Now, the thing is you have to write this template in a way that still allows for exploration. So that's where the specification in C++ comes handy. So with C++, you can actually create a very parameterized template with this matrix and vector unit that can, where you can change much higher level parameters, not at the level of loops, but much higher level parameters, and can generate many different configurations of the AI design, and then figure out, sort of explore that design space. So for example, in this template, we have this matrix unit for matrix multiplications and convolutions. We have this vector unit for operations after those matrix operations. You can fuse operations between matrix and vectors, so you can do a sort of a gem first and then follow it by some nonlinear operation. And then you can already in the template configure the sort of the schedule with which these operations run on these two units. So for example, let's say your matrix multiplication is a bunch of nested loops. The template allows sort of changing the order of those loops and so on and so forth. And so you're kind of exposing the parameters that you would like to explore while leaving all of the tedious details of implementation to the template itself. So now with this template, we can actually explore the space at a much higher level. So for example, I can easily change the number of compute elements that I have in my accelerator. So for example, it'll change the size of the systolic array. I can change the memory sizes and bandwidths very easily. And that's the level at which I want to do exploration. I don't want to do exploration at the level of loops and pipelining and so on. I can change the data types very easily. So let's say I have my processing element and that has some input and weight coming in, gets multiplied and added to some partial sum. I can say, okay, I want them in floating point, or I can say I want them in lower precision floating point. I can have mixed types. So inputs and weights can be one type, partial sum can be another type. I can do vectorized type. So I can say, okay, I have one weight, but I have 4 inputs coming in, so create a vector data path. And then I can also add support. So in this template also add support for different quantization schemes. So for example, you're doing like this partial sum in int24, but then you want to go to a floating point representation to do vector operations. So you can conditionally introduce or not introduce logic based on what you want to explore. So the way we have written this template essentially allows you to explore this space much more easily than at the level of loops and pragmas and so on. Okay, so that's the main point. Now, how do we do this? We essentially do this by using C++ templatization. The way you do this is, let's say you're writing a function, right, in C++, instead of specifying the type that it operates on, that type is parameterized. So this type here is just t. Now, I can do my max on 2 integers or 2 floating points or 2 arrays of vectors. That can be plugged in later by the compiler. So the compiler can later on do type substitution based on what exact parameters you have selected. These types can also be arbitrary. So you can define your own class, and then you sort of substitute that class in later. And so that is the precise mechanism for how we have created this parameterized template. And this is much more general than sort of most other prior work, which maybe hard codes it for integers or different precision of integers or floating point and so on. Here, you can have essentially arbitrary data types and so on. So for example, I can, my data type could be like a vector of some type t, and that it'll work. Or it could be different types for input weights and outputs and so on and so forth. All right. So with that background in mind, here's this template. What does the full flow look like? So you start with some architectural parameters. I haven't told you where these parameters come from, but that's the high-level specification that the user gives. And those feed into this template. And then a C++ compiler will do substitution and kind of create a specialized design that has your parameters. And you can basically run, it's just C++ code. You can run simulation on it with some test, figure out your model accuracy on an entire data set. And then you can push that C++ specification through high-level synthesis and generate Verilog. And then it goes through your normal physical design flow, like nothing special after you have Verilog. So you can do logic synthesis, you can do place and route, and so on and so forth. The nice thing is that high-level synthesis will take your a characterized technology library, and you can tell it, generate this frequency for this technology, right? And it'll automatically generate pipeline RTL for you. So that is very high, also parameterized at a very high level. So far so good. So what this allows you to do is go from some specification like, I want 1024 max with these many kilobytes of memory with this hierarchy, working with 4-bit integers, and so on. And this is all you say, and out you get a functional AI accelerator, right? So that's pretty significant automation with this flow. But the issue is that that's not enough. In order to actually make this useful, you still need a way to test your chip for different AI models. And for that, you need to map your AI model to the instructions of this accelerator. So what we ended up doing is essentially creating a complete compiler that maps models to the accelerator. So what does this compiler do? Well, it starts from a PyTorch model. So this is just a simple, it's a 2-layer neural network with 2 fully connected layers. This is like actual code. And we take this PyTorch model through Torch Dynamo, which is a PyTorch 2.0 sort of function. And it converts it into a static compute graph. This is what that graph looks like. You can imagine this graph being, like some tensors flowing in, going into a convolution, coming out, going into ReLU, going into another convolution, and so on. So it's like a data flow graph of operators happening on your inputs and weights and biases and so on. So you get this graph. Then what you have to typically do is do some sort of quantization, which means going from a floating point model to some much lower precision floating point or some lower precision integer data type, to using those data types. So you can specify that at a very high level. You can say that, I want to quantize this to this type. And you can specify different types for different layers. You can specify different types for like even the different operands within a layer. So you can do very fine-grained specification of quantization. And then the compiler is going to then change the graph to a new graph and kind of insert quantize, dequantize operations wherever needed. And then typically, you can execute this, but this might be inefficient. So you do another step, which is called layer fusion. And what that does is it takes many nodes and then kind of collapses them into a single node that can be executed in one pass on the accelerator. So for example, if you're doing matrix multiplication and then a ReLU, you typically don't want to go back to the memory between the matrix multiply and the ReLU. So you kind of read the inputs in once, do matrix multiply, and then kind of do ReLU in place on the output, and then send that back to the memory. That's called fusion. So the layer fusion node takes in some specification of what can be fused in the hardware, and then looks for those fusion opportunities on the PyTorch, on this graph, and creates these collapsed nodes for everything that can be fused together. So now you have this fused graph. You're still not done because the tensors that you're working with might be too large to fit on your on-chip memories. So now what you have to do is scheduling, which is you're tiling the loops and reordering the loops and so on and so forth. So you have to go through a scheduling and memory planning stage. And the important thing is that that scheduling depends upon the hardware parameters again. So similar to Fusion, how to tile will depend upon what the memory sizes and bandwidths and so on are. So this particular stage is going to take in those same architectural parameters that were fed into the hardware generation flow, like how big your array is, what your memory hierarchy is, and sizes and bandwidths and all of that, and then determine the best sort of tiling strategy. And the way it determines the best strategy is by we create a performance model of this accelerator as well. So the same parameters that parameterize the Verilog or HLS model also parameterize a performance and energy model. And so now you have a mechanism to say, test different tiling strategies and pick the best one based on the model. So we do the scheduling and memory planning, and then finally we have to map the instructions and so on, generate code. And then how do you do design space exploration? The way you do design space exploration is by adding another outer loop of search over these architectural parameters. And you can do that because you have a full compiler to map the DNN model. So for example, I have one set of parameters. I can figure out, using my compiler, what the performance is, what the energy is or what the accuracy is of my model on these parameters. I can change the parameters and figure out how those parameters, how those metrics change. So now onto some results. So we've used this generator for taping out or for generating designs that have been taped out in several chips. Here are some chips. I'm going to show you some, what you can do with this. So the first thing that you can do is basically this design space exploration that I talked about. So for example, we can study the effect of different resource types, particularly quantization schemes and data types. And then we can also study resource allocation, like how big of a chip to design, and then what performance will you get in return. I'll show some comparison with some of the prior generators, with some hand-optimized accelerators. So this system is useful only if it generates designs that are as good as hand-designed things. And then finally, I'll present some slides on how do you use this. You can actually also use this as a benchmarking tool. So the background is that, let's say you have a non-digital, some non-traditional way of doing AI. Great. But you still want to know how that non-traditional way would compare to a digital accelerator. And typically, the problem is that you don't have a way of generating an ISO area, ISO Mac, ISO this digital accelerator, right? Because the designs that are out there might be very different in the data types they use, the scale they have, and so on and so forth. And so you want a way to easily generate, reasonable digital baselines to compare your non-traditional design with. And now we have a generator which can, generate designs with arbitrary parameterization. So you can use that as a way to create comparison points for non-traditional AI technologies. So I'll show you some results there. OK, so the first thing that we can do, for example, is study the effect of quantization with different types. So here's a whole bunch of models. Here's a whole bunch of data sets. Different scales of models going from small models to BERT-based, which is reasonably large. We have some work on LLMs as well. It's just not on the slide. And here what we are saying is that, OK, the traditional types are FP32 and bfloat16, and they get reasonably high accuracy. But let's say I want to find an 8-bit type that gets me to a reasonable accuracy. So you can explore different types, floating point 8, int 8, microscaled int 8, and so on and so forth. And the system allows you to very precisely say what your accuracy is going to be for the data type of your choice. You could also create a type of your own. here's my new type, and the tool will allow you to tell, the tool will give you what the accuracy is. And then you can, now since you can generate RTL, you can also synthesize it. So you can not just figure out what the accuracy is, you can say what the area is. So for example, here are different accelerator sizes. So let's say, look,
Why do you need the HLS for the accuracy?
you don't need HLS.
Okay.
You just need a bit accurate C++ model, which our template provides. You don't need to synthesize anything. Good question. So now you can actually, now you need HLS. So for area, you do need HLS. So you can generate accelerators of different scales and then test out all the types. And something interesting here to see is that, while the floating point types are a little bit bigger, the block scaled int8 and int8 are, about the same. And in fact, for larger accelerator sizes, it's actually better to have block scaled int8 versus int8, which was surprising. The main reason is that with normal int8 without any scaling factors, you typically need to accumulate in a larger integer data type, and that leads to a larger accumulation buffer. But with the microscaled int8, you accumulate in a 16-bit floating point format, which leads to a smaller buffer. So it's kind of counterintuitive that you go from something that does not have any scaling factors to something that has additional hardware to deal with scaling factors, and you're saving area. So you can do these types of explorations. You can also explore around resource allocation. So here, I go all the way from an 8x8 accelerator to a 64x64 accelerator. You can go even further. And you can see, how's my performance looking? So for example, here's ResNet 18. Here's the runtime in precise number of cycles here. And you can convert cycles to runtime, absolute runtime easily, because you know what frequency HLS synthesized is designed at. In this case, it was about 1 gigahertz. And you can see that the designs that are produced by the generator are scaling pretty well. So you're going from 32 million cycles to 16 million cycles to 8 million cycles to 4 million cycles, right, as you're doubling compute. It's scales pretty well. And then with 64x64, it doesn't scale that well because now the network layers are, they're too small. And so now you have too much compute. And so things go underutilized. Yes?
So the capacity, the SRAM capacity, are the optimal size for that particular array size, or you'll explore that?
You can explore that. So here what we are doing is that as you have a bigger and bigger array, you should both grow the depth and the width of these SRAMs. Here we are keeping the depth constant and just growing the width. So we haven't explored the depth axis, but that's another exploration that you can do. You can say that, let's say for, I want to go with a 32x32 design that looks reasonable. Now, for the same compute, let me do an exploration over the amount of SRAM. And that typically, it doesn't have that much of a performance impact, but it has, for reasonable sized SRAMs, but it has an energy impact. So you can do another exploration on that. And I don't have that in the slides, but it's very easy to do that. And you can repeat this, you're not limited to one neural network. You can repeat this for ResNet 50, VIT, MobileNet, MobileBird Tiny, BERT, arbitrary networks. And what you can see on the slide is that the designs that are being produced are scaling reasonably well with very high utilization. So these dots show the hardware utilization. So what this means is that for this 32x32 design, the Mac units are utilized 98% of the time, which is reasonably high. Okay, so these are the types of explorations that you can do. Here's some comparison with prior work. Here's another generator called Gemini that is a chisel-based generator for similar problem statement. Generate different AI accelerators. And the HLS produced design is bigger than the chisel design. Much of this is because you're comparing something that is produced by an HLS tool versus something that was handwritten at the RTL level. But at the same time, it is much more performant. So your runtime is going from 43 milliseconds to 17 milliseconds, and so it is much better coded for higher performance. Okay, here's a comparison with another generator. This is NVDLA. This is a system Verilog-based generator, so another RTL-based generator versus an HLS-based generator. And what you can see is compared to this one, compared to NVDLA, ours is actually smaller, surprisingly. And it is much better performance. So we are getting lower area and lower runtime. So good on both fronts.
Why? I would expect it
Better design, right? Ultimately, the template is encoding some design, right? So it's just more optimized design. Okay, you can also compare, for the end product to be useful, it's not just fair to compare with generators because, people are not throwing AI specifications at generators and generating the chips that they want to ship in fabrication. People are, hand optimizing them because they are shipped in such large quantities. So here's some comparison with this prior work called Simba. And what we see is that, the good thing is that, this tool is very good for benchmarking. So let's say Simba had, integer 8 multipliers, int 24 accumulation, 16 nanometer technology, 1024 max, and so on. With our generator, we can precisely match these parameters, right? We don't have to compare apples to oranges. We can compare apples to apples. So we can precisely match these. So we can say, okay, same technology node, same types, same number of max, right? The only caveat here is that Simba is running at a much higher voltage and therefore achieving a much higher frequency. And we didn't have technology libraries characterized at that voltage. And so, we worked with whatever libraries we had, which were at 0.8 volts, which is actually the nominal voltage at 16 nanometer. And what we see is that we are getting a design that is, reasonably matched, actually lower in latency, even though we are running at such a, lower frequency. Like this, it's almost a 1.8x in lower frequency. And we are still beating in terms of milliseconds. So that basically tells that here, these 1024 max are not well utilized. So you have 48% max utilization versus 94% of this design. So the generator design is, comparable or better than some hand-optimized designs. Here's another hand-optimized design, and this one is better optimized. And you can see that, again, for similar configurations, the latency is actually quite close. The prior work actually does not accelerate all the operations. So these numbers are on, the Voyager number is on the full network, whereas the other number, omits some layers and so on. But it's close.
Why don't you measure
energy efficiency? It's harder to measure energy efficiency. You can. It just takes more time. So the problem is that you need to do some sort of power simulation in order to get to the energy efficiency number. And unfortunately, that power simulation, like at the HLS level, it's super off. So you have to do it at least at a logic synthesis level. So you take the post-logic synthesis netlist, and then you annotate it with activities from RTL simulation, and then you get power, and then you get energy from that. So those experiments take a lot of time. So we just didn't have the time to run those. But you can. So if you had the time to run power simulation, then you can do energy efficiency comparison. But take it from me, if you have a very good utilization, you're going to have better, like if you have a design with much better utilization of the hardware, it'll typically be more energy efficient than the one
I
that
agree,
does
but
not.
then you probably want to optimize for energy efficiency, right?
Yeah, I think optimizing for energy efficiency requires you to speed up the process with which you are determining energy efficiency for one point. And I think the way to do this is by creating some, like for example, we have some coarse-grained energy models, that do things like, okay, here's different memory sizes, and then here's different amounts of compute, and here's the energy per operation or energy per access, and you do some coarse-grained calculation with that. So we have some coarse-grained models, but the thing is, if you're comparing to prior work, you can't compare measured energy number with this coarse-grained model. Well, I mean, you can, but it's going to be super off. So what you need is some more precise energy models that allow you to do this comparison and exploration faster for energy. For performance, we can do things reasonably fast because you don't need to do synthesis. You do logic synthesis. You have to do HLS, but you don't have to do logic synthesis. So and RTL simulation runs reasonably fast. Power estimation takes even more time. So it's just a matter of how much time you want to run these systems for. Okay, so in the last few minutes, I will give you some more things that you can do with this generator. So I told you that we can use, actually I forgot to mention, this system is called Voyager. So we can use the Voyager system for benchmarking. And the reason I think this is very important is because, sometimes you read a paper, it's very difficult to figure out where the benefits came from. So I'm 10x better than this other prior work. Okay, where is this 10x coming from? This prior work is in a different technology. It has a different amount of compute. It has different memory sizes. It has different data types, right? So figuring out where that 10x came from is very important. And you need a way to be able to decouple the impact of the scale of the hardware and the technology of the hardware and so on from perhaps the detailed architectural innovation in that hardware. And most prior work will report absolute numbers, like here's the latency on this network, okay. But you have to normalize for all these other things. So the way you can use Voyager for benchmarking is by generating, similar to how we did, baseline designs that are matched in the amount of compute and memory and so on and technology to the design that you want to compare with. And then do a more apples-to-apples comparison. So here's an example. I could have picked anything. I picked one paper. So here's a SOC, published in JSSC, so trustworthy. And it has two things. It has a digital accelerator, and it has a in-memory computing accelerator. Okay, fantastic. The way this particular paper reports numbers is that it says, okay, we have this digital accelerator and we have this in-memory computing accelerator. Our in-memory computing thing, like if you use that together with the digital, I'm so much better than using the digital alone, right? It seems reasonable, but the question is, well, how good is that digital accelerator? And then, in the same area as the in-memory computing thing, could you have done, an equivalent digital accelerator that's probably much better, right? So, so you can answer that question with the system. So for example, here is the digital accelerator. It's in 22 nanometers and int8, running at this particular 270 megahertz frequency, this voltage, 256 max, and so on. So what we can do is, okay, we can ask our generator to sort of match these design parameters, same technology, same type, same frequency, same max, similar as RAM capacity and so on. And then we look at performance. So they report performance on this ResNet 18. So we say, okay, what is the ResNet 18 performance? And so what we see is that we can produce a design that runs ResNet 18 in 29 milliseconds versus 63 milliseconds. Okay, so that's a factor of 2 right there. Like the baseline is off by a factor of 2 from what you can do with the same amount of compute in the same technology at the same frequency, right? So this is useful.
How they design it works out.
I don't know. Okay, so now you say, okay, now I'm going to take the final numbers, digital plus in-memory computing, the final, like the numbers on which the paper was published. Right, so 22 nanometer. Now the data type is with in-memory computing, you know, it's a bit weird, right? It's not int 8, it's something in between. So it's anything from int 1.5 to 8. We say, okay, fine, I'm not going to bother with this int 1.5 to 8, I'm just going to use int 8 because, you know, how do you do int 1.5 in digital?
Won't that be reflected in the accuracy parameters?
Yeah. So,
We'll come to that.
yeah, we can. Well, I don't have it in this table, but we can come to that. So, okay, so we say, okay, fine, similar specifications, same frequency, same voltage, and then they have a ridiculous number of max, 37,200, that many max per cycle. And we said, okay, fine, I don't want to spend the HLS time, HLS tool generation time to generate that many max. So let me start with something small and see where it gets, and then I'll scale max. So I just put down 2048 max. So our design is smaller in terms of number of max, similar SRAM capacity and so on. Okay. So even with 2048 max, I'm getting a latency of 3.92 milliseconds rather than compared to 3.6 milliseconds. And you know, this is with a much larger Mac. Instead of increasing the number of Macs, I say, okay, well, you know, I'm not limited to 270 megahertz. In 22 nanometer, I can run at a higher frequency, right? So I can run this design at 640 megahertz. And then I'm already at 1.65 milliseconds, which is, you know, much lower than 3.6 milliseconds. And I could have increased the number of Macs and, you know, kept the frequency the same if, you know, I had to focus on energy consumption or something like that. But essentially, what this is enabling you to do is, you know, taking any arbitrary paper and then generating a design that is matched in specifications to that paper and being able to say, okay, is there a benefit to this technique? And there could be a benefit to that technique. It's just that implementation, you know, doesn't show it. But, you know, it's still a useful way to, you know, be able to, you know, read and compare research papers. Yes.
I fully agree with you that, you know, there are lots of issues with these numbers people are reporting, so it's very useful. Just an inquisitive question: if now that you have a better digital kind of a backbone,
Yeah.
let's call it that way,
Yeah.
and if somebody now try to insert kind of the specifications of their in-memory computing, let's say in your better digital backbone,
Yeah.
do you see any benefits for that?
I mean, we'll have to do that experiment.
Yeah,
so
absolutely.
this system
You guys
can't,
do it yet, yeah.
you can't insert in-memory computing into the system. It's just a C++ model,
Understand.
right? But you could say, okay, here's the better digital backbone, and I'm going to use all of this and just, you know, hand design an accelerator that substitutes the Mac array with an in-memory computing core, and perhaps that'll lead to a benefit, right? I'm not saying you shouldn't do in-memory computing. I'm just saying that, you know, we have to do better benchmarking of in-memory computing.
In your evaluation, does it consider also like the data movement in the performance?
Yes, of course. Yes.
So if you do in-memory computing and another accelerator, the data movement between the two accelerators is calculated.
Well, here it's just one accelerator, right?
No, but
This is on chip.
Data movement between memory and
On chip, I mean,
compute.
yeah.
Memory and compute is calculated. Yeah, and you can factor in DRAM to accelerator data movement also. And in fact, you know, I'm pretty sure this 1.65 will include that because this is a compute-bound model, and so you can hide the DRAM to compute data movement.
It's in memory like SRAM, that it's the same cache, or it's the separate module.
Same on-chip memory, you know.
Yeah,
same
it's
on-chip
the same
memory.
module, basically.
You remember this is the question I was asking on
Yeah.
Monday to the speaker
Yeah.
sitting there? That's exactly what it is.
Yeah, so same on-chip memory, 708 kilobytes
Okay.
compared to
Yes, it's
768
So they
kilobytes.
just added the computing capabilities to the SRAM.
I think
Well,
probably.
I don't know what the implementation was here and whether they'd added.
logic, okay.
I have to mention that I think ResNet 18 is a compute-bound case. It's not a
Right.
data movement-bound case, so probably that doesn't matter.
Yeah, it doesn't
It's
matter, but you can
competition.
take that into account, like no problem. In fact, our performance model takes even the DRAM to on-chip data movement into account. Okay, I'll give you another example.
So can I?
Yes.
Maybe I missed so if I look at the Voyager here,
Yeah.
the latency is bottom line is 3.92. And I think a couple of slides ago, you have another Voyager design.
Probably the parameters are a bit different.
Is that the parameters are different?
Yeah, probably the parameters are different.
Okay.
It's probably consistent. Okay, so here's another experiment that I wanted to do that bothered me for a while. So in AI accelerators, we mentioned that we can do quantization of models to get hardware efficiency. The other thing that you can do is introduce sparsity in your model, and then design hardware that is dedicated to accelerating those sparse matrix multiplications and sparse convolutions and so on and so forth. While that sounds fantastic, the problem with introducing sparsity is that your hardware becomes much more complicated than simply a quantized model. So one very interesting question is, for the same area budget, is it better to just do a quantized model for the same accuracy, or to have this extra hardware and then introduce a lot of sparsity? And which way is better, or perhaps there's a middle ground. So we picked a published SoC out there that has this sparsity and hardware for sparsity. And we generated a design that tries to match the parameters. Of course, it's not the same design. One is sparse, one is dense. But same frequency, voltage, similar number of max, and so on. And we looked at the latency, and we said, OK, it's instead of 11 milliseconds, it's 35 milliseconds. So clearly, the sparsity has a benefit. But the dense design is much smaller, right? Instead of 2.4 millimeters square, it's just 1.1 millimeters square, right? So I can put more of the dense in the same area, right? So, and the other thing that I can do is, since my design is not sparse, I can do more quantization, right? So first, what I can do is just go from int16 to int8. My area decreases even more. Latency doesn't change because the number of max are the same. I can, in fact, for this particular ResNet 50, I can even go to int4 and get this 9.24. And at the same time, what I can do is I can increase my max per cycle without blowing up my area. So now what I have is a design that is still smaller in area. It has more max, but it's still smaller in area, and it's getting a better latency. And in fact, I can actually run this design much faster. We don't have to limit ourselves to 480 megahertz. And so I have now a design that is, smaller and faster, and it's dense, so it's simpler, right? So again, this kind of shows the utility of this tool as a benchmarking system to see if certain architectural ideas are worth it or not, right?
Do you also report the accuracy here? Do they all have, do they achieve the same accuracy or accuracy?
I think we had to do some. We'll have to do some digging for the accuracy, but like for ResNet 50, I can tell you that up to int4 quantization it works.
So it doesn't matter what is also the accumulation data type?
I think accumulation data type matters. I think you can go up to int16 and you should be okay. I think below int16 it becomes harder. Right, yes. Okay, so I'll conclude. So what did I do? I presented a methodology for exploring this design space of AI accelerators and generating tape-out ready hardware. You can explore along the scale of the accelerator, memory hierarchy, data types, scheduling, and so on. How did we do this? We leveraged modern HLS tools, but just the HLS tools are not sufficient because it's very hard to write HLS in one shot. That is also performant. So we created a template that hides the effort of writing that sort of cumbersome HLS model. And then in order to make it useful, you also need some sort of software, right? So we designed a compiler that allows running DNNs end-to-end on any instance of the generated hardware, not just one hardware instance. And the results show that our work outperforms existing generators, and it matches many of the handwritten designs that are out there. And furthermore, it can be used as this benchmarking tool for non-traditional AI accelerators. So I'll end with that, and I have 10 more minutes for questions.
Great talk. Thank you. I really enjoyed it. A couple of, I wouldn't say tough questions, but looking at the future. Okay, in the end, you would like to design large chips.
Yes.
And so you will need to have some layout awareness, because
Yes.
you cannot forget about that stupid wire that it goes across the
Yes.
track.
Yes.
What are your thoughts of including some layout awareness into
Yeah.
this?
Yeah, I think some of the layout awareness is considered in the decisions that we took while creating this template. So we specifically went with a systolic design. And with a systolic design, you are already, minimizing the number of wires that you have. Like, it's not an n squared problem, it's an n problem instead of an n squared problem. And then for very large chips, actually, the system is insufficient, because in a much larger chip, you typically not have one humongous systolic array. You typically have a reasonable size systolic array and then multiple of those. And so you need to extend this generator to be able to generate those multi-core designs. So I think that's what's needed for very large chips.
So this brings me to the second question, just looking at the future. If you have something very large that in the end will tend to be heterogeneous because you don't have these systolic arrays all over,
Yeah.
you will actually combine all these various processors with a network on chip.
Yeah.
And you will have to be able also to bring this into the equation.
Yes.
Now, one way in which it is done now is that you bring in the knock at the last moment. If you
Yes.
use like Accelerators, you just design the various parts. But in what you present is basically you want to be able to reason and to think of where
Yes.
things are. So kind of the networking and the LHOS
Yeah.
are at the same level. Do you
Yeah,
have
yeah,
any
yeah.
thoughts?
Yeah, I mean, that's, again, work that we haven't
It's
done
very
yet. But
open-ended.
yeah, but you'd have to do that. Essentially, you can use this tool to generate, stamp out multiple cores, but then you need a way to estimate the performance and area and power of that knock as your system is scaling. I think that requires some more modeling effort, to be honest. And it really also depends upon that, like the precise knock topology you're using. Are you doing all-to-all? Do you have some sort of grid with routing in it, and so on and so forth? So you'd have to think carefully about those types of things. And I'm sure we can create a generator where you can parameterize over the knock parameters and size and so on and so forth, and be able to do some exploration. Yeah, but what we have found is that for reasonably large systolic, so 64 by 64 is kind of the sweet spot for systolic array size. If you go to 128 by 128, most layers underutilize it. So you see that the utilization for many networks drops as you go to larger systolic arrays. So this system can generate reasonably sized systolic array. Well, it can generate the bigger ones, but they're not useful. And then you have to go to multi-core for bigger things. Yeah. So yeah, definitely interesting future work.
So better forward-looking, maybe.
Yeah.
So you focus mostly is on DNNs, and
Yeah.
it's really good with convolution and
Yeah.
matrix. Do you think this can be extended to more, other type of neural network models,
Like,
not in this current form, right?
The template essentially is hard-coded for something that has matrix multiplications, convolutions, and subvector operations. So if the fundamental operation is not matrix multiplication or convolution, then that template is not very useful anymore.
Yeah,
So you'd have to write a new template.
Right, but can your template be easily extended to include some other type of element?
I mean, if it kind of fits in a similar pattern, like if it's a systolic array of, not a MAC but something else, sure. I think that is very easy to do. But if it's a fundamentally different hardware architecture, then, you can't reuse much of this. You'll have to write a new template instead. And much of the work here was writing that template and making it performant. And so, this is tailored for DNNs, but the good news is that there are a lot of DNNs and most people are interested in DNNs, and so it's okay to specialize for that. Yeah. Okay, I think that's the end. Thank you.